Have you ever heard Invert Binary Tree called the Hello World of Binary Tree questions? It's a classic Pattern Mastery 100 favorite, frequently asked at Google and Microsoft, and surprisingly, it still trips up more than 25% of candidates. Master this problem, and you'll build the foundation for tree recursion, traversals, and more. Let's approach Invert Binary Tree with a basic method, breaking down the process, analyzing key steps, and ensuring you understand every pointer twist. Let's break it down. Given the root of a binary tree, invert it, meaning swap the left and right child of every node in the tree. Input, binary tree root node. Output, the same tree, but with every left and right subtree swapped. Real-world example. Imagine an image editing app with a mirror filter. To flip an image horizontally, you need to swap every left and right pixel or object. Similarly, inverting a tree mirrors its structure. Interviewers may ask, how would you design a function to mirror a decision tree, or flip a UI layout that's stored in a binary tree structure? Let's assess it. What's tricky? Recursion is the natural fit for trees, but you need to ensure you swap every subtree, not just the first level. You can use DFS, depth first traversal, preorder, postorder, or BFS, level order, but recursion is clearest and most popular in interviews. Think step by step. If the current node is null, do nothing, base case. Otherwise, swap its left and right children. Recursively call the invert function on both children. You'll process every node exactly once, flipping the tree from the top down. Let's go deeper. If you prefer iteration, you can use a queue, BFS, but recursion matches how we mentally walk through a tree. Be careful to process null nodes and leaf nodes. These are your base cases. Here's some edge cases. Empty tree should return null. Single node should return the node itself. Skewed trees, only left or right children. Here's the structure. If root is null, return null. Swap roots left and right children, recursively invert the left child. Recursively invert the right child, return the root. Let's try to implement it using solution 1. Line-by-line narration, line highlighted, class solution. We begin by defining a class called solution, just a place to store our function. Pause. Line highlighted, def invert tree self, root. This function is named invert tree, and its job is to flip a binary tree left to right, like holding it up to a mirror. Pause. Line highlighted, if root is none, here we check whether the current node is empty. If there's nothing here, we have nothing to invert. Pause. Line highlighted, return none. When the node is empty, we return none. This acts as our base case for the recursion. Time complexity note. Base case is 01. Pause. Line highlighted, hash swap left and right subtrees. This comment tells us the main operation. We swap whatever is on the left and whatever is on the right. Pause. Line highlighted, root.left, root.right equals root.right, root.left. This line does the actual swap. Imagine taking the left child and right child of the node and flipping them. One clean line does it all. Pause. Line highlighted, hash recursively invert the swapped subtrees. This comment explains that after swapping, we still need to invert deeper levels of the tree. Pause. Line highlighted, self.invert tree root.left. Here we recursively invert the left subtree, which used to be on the right before the swap. We keep going deeper until we reach leaves. Time complexity. Every node is visited once, giving us on. Pause. Line highlighted, self.invert tree root.right, and we do the same for the right subtree, recursively inverting everything beneath it. Pause. Line highlighted, return root. Finally, after the entire subtree under this node has been inverted, we return the root so the inverted tree can rebuild itself as the recursion unwinds. Pause. Final wrap-up. And that's how this algorithm works. It first checks for an empty node, then swaps the left and right children, and finally recursively inverts each subtree until the entire tree becomes a mirror image. Efficient, simple, and elegant. Highlight input box. Root equals 4, 2, 7, 1, 3, 6, 9. Let's run our function on this binary tree. 4, 2, 7, 1, 3, 6, 9. This array represents a level-order traversal of the tree. 4 is the root, 2 and 7 are its children. 1 and 3 belong under 2, while 6 and 9 belong under 7. Explain the logic briefly. Our algorithm inverts the entire binary tree, meaning every left child swaps with the right child at every node. After inversion, 2 and 7 swap places under the root, then 1 swaps with 3, and 6 swaps with 9. Performing a traversal after this swap gives us 4, 7, 2, 9, 6, 3, 1. Highlight output box. Output, 4, 7, 2, 9, 6, 3, 1. Expected, 4, 7, 2, 9, 6, 3, 1. And that's exactly the result we see. The output perfectly matches the expected output. The test case passes with flying colors. So, our implementation is correct. The algorithm successfully inverts the binary tree and returns the correct transform structure, clear, efficient, and accurate. Now let's try another implement approach using solution 2. Line-by-line narration friendly, clear, step-by-step explanation. Like a coding tutor guiding beginners. Line highlighted, class solution. We start by defining a class called solution, just a container to hold our method. Pause. Line highlighted def invert tree self, root. This function, invert tree, flips a binary tree left to right, like holding the tree up to a mirror. Pause. Line highlighted. If not root, we check whether the root is empty. If there's no tree, there's nothing to invert. Pause. Line highlighted. Return none. In that case, we return none because the inversion of an empty tree is still empty. Time complexity. Base case is 01. Pause. Line highlighted. Q equals root. We create a queue starting with just the root. This queue allows us to explore the tree level by level using BFS, breadth first search. Space complexity. Can reach up to ON in the worst case if the tree is wide. Pause. Line highlighted. While queue, this loop keeps running as long as we still have nodes to process. Every iteration handles one node from the front of the queue. Time complexity. We process each node exactly once ON. Pause. Line highlighted. Node equals queue.pop0. We pop the first node from the queue. This is BFS behavior. First in, first out. This is the node whose children we're about to swap. Pause. Line highlighted. Hash swap left and right children. This comment previews the main operation we're about to perform, flipping the children of the current node. Pause. Line highlighted node.left, node.right equals node.right, node.left. This single line swaps the current node's left and right children. It's like flipping the branches of the tree on this node. Clean, simple, and powerful. Pause. Line highlighted, hash add non-null children to queue for processing. This comment tells us that after swapping, we need to continue the process down the tree. Pause. Line highlighted, if node.left, we check whether there is a left child, after the swap. Pause. Line highlighted, queue.append node.left, if so, we add it to the queue so it will be processed, and swapped, later. Pause. Line highlighted, if node.right, we also check whether there is a right child. Pause. Line highlighted, queue.append node.right, and if that child exists, we add it to the queue as well. This ensures we eventually swap every node's children in the entire tree. Pause. Line highlighted, return root. After all nodes have been processed and swapped, we return the original root, now representing the fully inverted, mirrored, tree. Pause. Final wrap-up. And that's how this algorithm works. It first performs a quick base case check, then uses a BFS queue to visit each node, swap its children, and continue level by level. Efficient, simple, and elegant. Highlight input box. Root equals 4, 2, 7, 1, 3, 6, 9. Let's run our function on this binary tree. 4, 2, 7, 1, 3, 6, 9. This array represents a level order traversal of the tree. 4 is the root. 2 and 7 are its children. 1 and 3 belong under 2, while 6 and 9 belong under 7. Explain the logic briefly. Our algorithm inverts the entire binary tree, meaning every left child swaps with the right child at every node. After inversion, 2 and 7 swap places under the root, then 1 swaps with 3, and 6 swaps with 9. Performing a traversal after this swap gives us 4, 7, 2, 9, 6, 3, 1. Highlight output box. Output, 4, 7, 2, 9, 6, 3, 1. Expected, 4, 7, 2, 9, 6, 3, 1. And that's exactly the result we see. The output perfectly matches the expected output. The test case passes with flying colors. So, our implementation is correct. The algorithm successfully inverts the binary tree and returns the correct transform structure, clear, efficient, and accurate. Alright, quick recap on Invert Binary Tree, the so-called hello world of binary tree problems. It's simple in theory but powerful for mastering recursion and traversal fundamentals. The task was to flip a binary tree by swapping every left and right child, essentially mirroring its structure while keeping all node values the same. We explored recursion as the clearest solution, noting that each node must be swapped and then its subtrees inverted. DFS and BFS can both work, but recursion keeps the logic clean and intuitive. Our plan was short and sharp: handle the null base case, swap the children, recursively invert the left and right, and finally return the root. We followed that plan in code, ran it on LeetCode, and it executed successfully with no errors. We walked through examples, confirming each node swapped correctly and all test cases passed as expected. The key takeaway? Recursion is about trusting the process. Solve for one node, let the function handle the rest. Mastering this mirror logic makes tackling more complex tree problems far easier.